shouldn't go there. But that's it. Oh, thanks. This is the things that this Orlov guy from materials engineering did was to use a powder technique, and he mixed the powder of small grains together with some particles that have coarse grain. Coarse grain means low plasticity, low yielding stress, and the rest that was a very fine grain makes material harder. And the mixity, they wondered if it would work, and they would like to know how the mixity should be, in what portions. And what you see here is this is the micrograph, and then the green particles are the coarse grain particles, and then the rest skeleton for some reason. I would call it just matrix, but the skeleton around here is of ultrafine grain and very hard. So this is what my student did. I'm going to talk about the finite element calculations that he did, and also some things that we discovered that made things very much more simple for the next generation of this work. So this is how we started. So this is a tensile test, or it's the metal is exposed to a tensile test, and the specimen is actually twice this. So this is the symmetry line in the middle, and it's pulled here in this direction. And then we think, I mean, it's very, it's artificially much the same. And we have traction free down here, up on the middle. That's the middle of the specimen. On top also, so there is another layer on top of this. And then we wanted to have something that would allow, because these foils that they do, they get ends with necking. So we would like to have a necking line possible to fit in here. So that's what you see. And this is the mesh and boundary conditions with symmetry boundary conditions up there and along here and along here. Here it's pulled, but otherwise it's symmetry conditions. And down here is the traction-free surface. So what we did was they had a difficulty determining what kind of material this is. So we got numbers, and numbers were given for yield stress and the immediate part down here. And then also another set of diamonds were applied to up here. And that gave us, because with the Ramberg-Osgood model, you can't have the, if you have a yield stress, you have to match it with their equation. So instead of doing that, we did this. This is for measurements down here, and that's for up here. And then we took intermediate materials also to give the guys at material science some chance of, or maybe use it with different materials. And this is the fine grade, the harder one, and this is the softer coarse grain. This is the result. So when things were pulled, they failed, and the elongation is what you see here. And the best part is if you get the largest elongation if you go for the pure coarse green. And this is the sorry. This is the pure skeleton, actually. This is the harder material. And this is the, is that correct? I'm not sure. Yeah. Oh, I see one thing. I thought I corrected that. This should be CG and CG here. So 0% of coarse grain is the harder material, and down here it's hard, but it breaks earlier. And there is a peak in the middle. So for around 60% of of coarse grain and ultrafine grain. The remaining 40% got the best results. And then you see there is a jump at the end. There is also, for the stresses, there is a jump at this end also. And to take a look at this diagram, this is for different percentages of coarse grain. And as you see, it looks, well, as I said, you have 77, which means 23% of 77% of coarse grain, 60%, and 40 is maximum. We saw 60 earlier, but that was because that was the list for ultrafine grain, actually. And then it decays, and then it jumps down to here. And if you have no grains at all, you get the higher, goes longer, and blood can stand for larger stress. And the person's in. I shouldn't ridicule people in material science. That's not my meaning. But they said that this is definitely wrong because you can't have a jump like that. Everyone in solid mechanics, at least, if you know your theory of elasticity, you know that if you put a tiny little hole in a sheet, you get 3 times higher and expose it to uniform tensile stress. You get 2 points, you get 3 times higher stress than the nominal stress. And then there is compression actually in the other direction, which was a very tragic thing for some guys at one of these platforms that we have in the North Sea. And they were going to install something, and then they drilled a hole, and they thought a small hole in a bone of this, what do you call them? Where you bring up the oil, oil, where they pump up the oil, the Norwegians. Oh, okay. But there was fatigue cracks. This small hole, and the entire bone was like this room or so. They thought, that's nothing. Doesn't matter, but that created a catastrophe that many people died. So that's that part. Also, when we looked closer at the, this is a unit cell. So here you have the coarse grain and coarse grain and coarse grain and coarse grain, and the rest is skeleton here. And this shows the plastic deformation, plastic straining. The thing that strikes you, that struck me when my student came back with it, was that you get this curvy. This is the lowest part of the model part. You see it's curvy because of loss of tractions. There is no, this is traction free, so it bulges out as it wish. But we would think that something would be happening up here. Here you see just little, and here perhaps, and here it's totally flat, which actually means that there is a symmetry line towards the second cell. Let me show you cells. So this cell row down here, this one already is a symmetry line, which means that all of the others will be exactly the same, more or less. Only down here where it's traction free, you will have, which meant for us also that we could just as well have done this just using 2 cells, one close to the boundary, and then all the rest will be the same. So we took a look also at the load carrying capacity of these rows of cells, and the first one is here, and this graph, the first half of element number, or unit cell number 1, and you see it's only 4% as compared to the nominal value. or 6% lower. And then this one is a little bit higher. So if you take the entire element, it will be like the others. Here, nothing happens. I mean, 6%. If you do finite elements, you don't bother with percentages below 1% or so. No. So this is kind of showing also that all of these could have been done just for one of them and separated from the rest. And this is what happens at the end. You get necking through the material. So this here shows necking lines that are forming and what it looks like down here. How is my time now here? I'm going. And then this is a table showing the angle towards the tensile direction. And this is on the deformed specimen, and this is on the not deformed. And you see it's between 53 to 60 degrees. So if you don't have the one with the thinnest skeleton, that one sticks out. But otherwise, it's exactly like what you get if you have a homogeneous material plate and you put it under tension, and the angle is 54.7 degrees. So it's like nothing happens because of that. So plane stress condition close to the traction-free surface boundary. That helped us to do a much smarter and 3D model because it will go faster. Only 2 cells have to be used. And then that's the conclusion of that. Coarse grain decreases strain never, even if they're very small. That's what I said before that. And then the necking. And this is it. Now I've used 60.
Good. Perfect.